Hello friends, so now let's start with the next session in the DC to AC converter, that is single phase full bridge inverter. Right now, in previous half bridge configuration, we had learned about how to convert DC to AC using the half bridge inverter. So in that, center tap supply or two identical supply with center tap was required, and load was connected in such a fashion that whenever a device conducts, the output is across the load. So at any time, only one power electronic switch was conducting, and two half capacity, that is Vs by 2 DC source were required, right? In single phase full bridge converter, we require only one supply of Vs capacity, and we require 4 switches. At any time, 2 switches will be conducting, and of course, as you can see in this circuit, only one switch in a leg will be conducting, because if both the switch in a leg will conduct, it will directly short circuit the source. So the load is connected here as shown. And most of the cases, load is going to have inductance. So we are supposed to have the freewheeling diodes also. And the freewheeling diodes I'm showing with red color like this. So they are connected in an anti-parallels across the power electronic switch. So here I have used BJT as a switch. We know we can use any self-commutating device like BJT, MOSFET, or IGBT, or for that matter GTU also. So these are the devices. We will name them T1 and T2. This is the pair which will be conducting at a time, and these are T3, T4. So the top inner leg, there are 2 devices. Top devices are generally given odd numbers, bottom are given even number. At any time, only one, right, inner leg will conduct, right? So we are supposed to understand only one power electronic switch in a leg will conduct at a given time. Right? And for the positive, negative half cycles, the pair T1, T2 or T3, T4 will be turned on, will be right. So and you have diodes also, so we'll label them same way: D1, D2, D3 and D4, right? So this is the circuit of single phase full bridge inverter. Now let's see how this is going to convert DC into AC. So single phase full bridge inverter is having a single source of Vs only. It requires 4 power electronic devices, T1, T2, T3, T4 with 4 freewheeling diodes, and we assume that load is going to be inductive. So we are expecting output over here. here. Let's say this is our positive direction of output, and the other way will be the opposite direction, right? So let's see the next picture. So in a single phase full bridge inverter, for positive half cycle, let us say that T is the time period of the output AC. Then for T by 2 period, so T1, T2, they are switched on for T by 2 period, and T3, T4, they are switched on for the other T by 2 period, and the same process is repeated for n number of cycles as long as you require the supply, right? So the waveforms which you get, or first let's see the circuit, and then we'll draw the waveform also. So when case 1, when T1 and T2 are on, so at that time what is going to be the situation, that this is BS, this is you can say T1 is turned on, and then you have this load, positive you are coming across over here, and this is negative, and then this is T2, and yeah, so this is going to be the circuit like this, and because of which the output which you get over here is something like this. This is the duration T by 2, and for that T by 2 period I have a pulse which is of duration Vs. This is the output voltage with respect to time. Okay, now what is going to happen to the current? So current is, it's an inductive circuit, this is an RL load, so current is supposed to build, but it is going to lag behind, is it not? And so when a steady state is established, current will be lagging behind the voltage. So the moment voltage is rising, current will not be rising, right? So now what is going to be the situation, that I0 lags behind V0. That is one thing, right? Now when after T by 2, right, at T by 2 or after T by 2 in time interval, when T1, T2 are turned off, V0 goes to 0, but I0 is still not 0, still a positive current is flowing through it. Now what is going to happen if there is no provision for a freewheeling diode? Then this positive current which is flowing through an inductor cannot be abruptly put to 0, otherwise it will lead to a huge voltage induced in that inductor, which may damage the power electronic switches, right? So but fortunately we have a freewheeling diode over here, so the current which was flowing in this direction, this is I0, is going to continue. Now how, in what fashion it can continue, that is what we are going to see in the next slide. So D3 and D4, see this is the load, and this is D3, so it will be forward bias, and D4 will also be forward bias, and the current which was flowing, this I0, it will continue, and it will complete the circuit in this fashion. So this is D3, D4. So D3, D4 will conduct for freewheeling duration. What is this? This is the time by which I0 comes to 0, right? So this is the second step, or you can say second phase of the operation. Now what is third phase? Third phase is that T3, T4 are turned on for time duration T by 2 seconds. Is it not? Now what is going to be the circuit when T3, T4 are turned on? So the load is over here. Yes. So keep in mind, when this is happening, voltage is negative. And current is positive. So it's conducting in this fashion. This is freewheeling action. I hope this is understood. When the freewheeling action, after the freewheeling action, T3, T4 comes into picture. So this is on switch T3. This is on switch T4, and this is the supply Vs, DC source Vs. So now this is going to give a negative pulse V0, negative output voltage V0, and current also is going to start flowing in the reverse direction after the freewheeling action has completed. Is it not? So this is going to ultimately, the output voltage is going to be like this. This is time. This is V0. This is Vs. This is minus Vs. Minus Vs. And this duration is T by 2. Duration is also T by 2. This is 0. Okay. So this is the third case. Now, when after T, what is going to happen? T3, T4 are off. So once again, V0 goes to 0. But I0 is still not 0. It is a reverse direction, or negative current is still flowing, and that is the freewheeling action. That freewheeling action will take place through D1, D2, right? So let's see the fourth and last case. So that freewheeling action is going to be the current through this load, which was flowing in this direction. It should continue unless the energy stored by the inductor is 0. So it is going to continue, and it is going to be like this. This D1 will be forward bias, and D2 will be forward bias. The circuit will be completed in this fashion. D1. This is freewheeling action takes place. At that time, the voltage has already become the positive, but the current is still negative. So that is going to be the case when D1, D2 conducts, right? So D1, D2 conducts in this case. We call it case number 4, right? So this is how you can see that when a steady state is achieved, we get the current waveform of RL load, where current will be lagging behind the voltage. Now let's see all the waveform in one circuit. So initially, let's say this is the say for base current IB1, IB2. So this is the duration for which it is on. Then how much is this? It is T by 2, then T by 2, and then it continues. Okay. Similarly, the pulses to the base of T3, T4 will be in this fashion. This is IB3, IB4. This is once again T by 2. This is T plus T by 2, and so on. Right? So output voltage is going to be something like this. Where the maximum value is going to be Vs. This is output voltage, and the output current which is more important for the study. We are assuming this is under steady state, where the circuit operation is taking place for a quite long time in steady state, and under this situation the waveform is drawn. Right? So these are the locations. This is the duration for which T1, T2 is on. So voltage is positive and current is negative. You can see current is increasing in this. This is current I0. This is the duration where T1 and T2 are on. This is the duration where voltage is negative, but current is still positive. So this is D3, D4 on. And this is last duration where T3, T4 is on. Right? So likewise, current is following in this fashion. Right? It is between two limits, say I1 to I2, positive and negative. So current is lagging behind the voltage, and you can see all the four devices, that is 4 diodes and 4 power electronic switches, they are conducting in different durations as shown. Right? The amount or duration depends on how much is the inductance of the circuit. Right? So that's how the waveforms of the single phase full bridge inverter looks like. Okay. Now let's see how much is going to be the output. So finally, we know that Vrms is nothing but 1 upon T by 2 integration 0 to T by 2 the output, that is Vs square, dt, and the whole raised to 1/2. If you evaluate, this comes out to be Vs. So RMS value is equal to Vs. Now, if you apply, see, this is a square wave, and you are intending to get a sine wave, right? So if you apply a Fourier series analysis, and if you find out the first fundamental, then V1 RMS, this capital V RMS is RMS value of a square wave, but sine wave, fundamental sine wave RMS is going to be 4Vs divided by root 2 pi. For a given square wave, if you apply the Fourier series analysis, you can very easily find out this, and this comes out to be approximately 0.9 times Vs, right? So this is RMS of the fundamental component of the sine wave. I hope you understand any periodic waveform can be thought of as a made up of fundamental sine wave and its multiple harmonics, and using that logic, this V1 RMS comes out to be like this, right? We also define total harmonic distortion, THD, is total harmonic distortion as square root of V RMS square, original waveforms square, minus sine fundamental V1 RMS square, and divide by V1 RMS, right? And for percentage, you can multiply with the 100. So this comes out to be 0.484843, sorry, or 48.43%. That is the percentage total harmonic distortion in the output of a AC, which is produced by single phase full bridge inverter. Right? So this is how the single phase full bridge inverter works. Let's see the whole concept once again. So this is single phase full bridge inverter. It is having the advantage, it is requires only one, you can say, DC voltage source, and the maximum voltage also you get is Vs, which is double than the half bridge. Here you require 4 switches. There are 2 legs. At any time, only one switch in a leg is conducting, but the total circuit gets completed when a pair, that is T1, T2 or T3, T4 are conducting, right? The diodes D1, D2, D3, D4 are used for freewheeling action when you are expecting the RL type of load, and the operation is explained like this. When the first turn on is there, T1, T2 are turned on, then freewheeling action, then T3, T4 are turned on, and this is the last freewheeling action. And these are the waveforms of the single phase full bridge inverter. This is with RL load. Right? So this is most common type of load, and that's why we are drawing the waveform with RL load. So these are the, you can see we have achieved AC with the help of this circuit. So DC to AC conversion is achieved, and this is the RMS value of the square wave, RMS value of the first fundamental, and total harmonic distortion of the circuit, right? So that's all about the topic, that is single phase full bridge inverter. It is having advantage, you get more RMS value, more maximum value, and the only thing is that you require more devices. Instead of having only 2 devices in half bridge, you require 4 diodes and 4 power electronic switching devices. So that is, the cost is going to be more, but output is also more, right? So that's how you can learn about the inverters. We'll continue with more of it in our next class. I hope you enjoyed this video. Thank you.